Due to the time, I would like to welcome you for the first session under the heading of Transportation System. I'm the chairman, Sven Körner, and due to the limited time of the presentation as well as the questions, I would just like to give a very short introductions of the next speakers. So we have only about 10 minutes time for the presentation, and I will give you a sign latest after 13 minutes. And at the end we have the chance to ask questions, and then we need to switch quite fast. First of all, I'm quite proud to introduce a colleague of mine, Mr. Eckhard Fritz. He is a system engineer and a specialist for propulsion systems of conventional and high-speed railway systems, as well as magnetic levitation systems. And he prepared a presentation about the energy consumption of high-speed systems, maglev systems compared to wheel. Mr. Fritz, please give us your presentation.
Thank you for your kind introduction. Ladies and gentlemen, welcome to my presentation. Energy consumption will be the focus for the next 10-15 minutes. Maglev systems in comparison with wheel rail systems. We all know energy consumption is an important part of the total operational cost, but a system decision, of course, should be based on a complete life cycle cost analysis. And so in the past, there were a lot of comparisons of maglev systems and wheel rail systems within, of course, all German maglev projects, and there were a lot of additional investigations also for potential international application lines. I was myself involved in a lot of such comparison, in a lot of such studies and investigations. And now in the focus, of course, is the construction of the new Shu Shinkansen line between Tokyo and Nagoya, and the planning of the Baltimore-Washington line. This was a drive for a new objective comparison, and our first question was, are exact, calculated, measured values available for a probably correct objective and a distortion-free comparison? The main influence parameters of energy consumption in general for every high-speed system is, of course, the top speed, the routes itself, the intermediate stops, the distance between the stops, the percentage of tunnel, important for the new Japanese maglev line, and particularly for the maglev systems, of course, the design of the traction power supply system itself, the train configuration, and very important for the conventional comparison based on seats, is important to know the ratio of first and second class and the total capacity of a train itself. We selected the shown systems which have been in trial or in operation for many years. We select the German ICE, the French TGV, and the Shinkansen N700 for the conventional high-speed lines, and for maglev long starter systems. Of course, long starter systems, we talk about high-speed passenger transportation, the German maglev Transrapid, and the Japanese MLX, respectively Shu Shinkansen system. Our comparison mainly based on the following routes. The data were a lot of own simulations, a lot of own studies, a lot of scientific papers, conference proceedings, and scientific books. You see a lot of different lines, long lines, middle long lines, and I will say also a short line if you think about high speed. The next challenge is how we can calculate and how we can display such an energy consumption itself. The first result, the first simulation result is of course the absolute value of energy consumption. This is the most honest value from the physical point of view, but this is a little bit inconvenient to use this parameter for energy consumption comparison. The most conventional parameter is a specific energy consumption based on seats and kilometer, often used by the industry, often used by publications and something like that. But as we know, the seats and the ratio of first and second class and probably third class, it's in operator's hand. And so this parameter is not distortion-free from the point of energy consumption. The next possibility, of course, is specific energy consumption based on tons, based on the weight and kilometers. This is probably convenient for freight trains, but not usable for high-speed passenger trains. And at the end, the main goal is to find a way to compare specific energy consumption of different high-speed systems without any distortion of results. What were our conditions? We only consider the secondary energy consumption. That means we did not consider power plants and cables, high voltage cables between the power plants and the substation itself. We considered, of course, the traction and the auxiliaries, and we defined the comparison interface at the middle voltage level of the substation. That means for the German ICE, the 15 kV level with 16.7 Hertz. The simple graphic shall show that in general both systems consist of similar equipment. You find inverters, you find transformers, you find a catenary system which could be similar for a feeder cable and something like that. This is the first result based on the conventional basis, based on seats. As I mentioned, it doesn't work. Sorry for that. Okay, we are here. This is based on seats. This is not distortion-free, but anyway, we use this as a first step. The different colors represent different systems. Detailed results you can find, of course, in the proceedings. To mention is here a lot of values in the range of the top speed between 300 and 330 for the conventional system, and the highest expected value, of course, for the Shure Shinkansen line because of the top speed of 500 kilometers per hour and the line nearly almost complete in the tunnel. And this is an excerpt from the previous slide. The blue color represents the system's comparison at the basis, at the level of the top speed of conventional high-speed systems. You see here the lowest value represented by the transfer bit. And what is in addition worth to noting here is that between the transfer bit at the top speed of 430 kilometers per hour and the ICE at its top speed of 330 kilometers per hour, the difference are of course 30% in the top speed, but only 7% in the energy consumption. This is valid for a long distant line here presented for the Hamburg-Berlin line. The results stand here for the transfer bit and also for the ICE for the Hamburg-Berlin connection. And it's impossible to... Oh, yeah. The next step was to define a so-called system typical effective area. What means this? That means we know the technical area and minus the driver caps, minus the crash zones and minus the required auxiliaries within the train, you can get for every train a so-called typical effective area under consideration of the train configuration itself. And based on this parameter, you can calculate a new energy consumption. And you see at the top speed of real rail systems at 330 kilometers per hour, the values become more similar. That means there is no advantage for every system at the top speed of wheel and rail. Of course, if you increase the top speed, the energy consumption rises up. This is, of course, the driving resistance and particularly for the Japanese systems due to the tunnel sections. This is the overall for the previous slide. I don't want to explain it in detail. You can find it in the written paper. I will explain the next step. Based on the typical effective area, you can standardize this effective area. Here, this is calculated for a 500 square meter effective area. And here, at this comparison, you see that there is a little advantage for the conventional high-speed systems at the top speed of 340 kilometers per hour. And both maglev systems, the German and the Japanese one, becomes also more similar based on this comparison parameter. This is distortion-free. There is no influence of the seats, no influence of the number of first and second class at all. Main results: specific energy consumption based on seats is not distortion-free. Is it possible to calculate the energy consumption based on an effective area? And some remarks to the new announced high-speed train generation by Alstom and Siemens. Both announced new types of trains, high-speed trains, which shall be decrease the energy consumption by 30 or 20%, but we have to notice there are still announcements, no detailed data available, no simulation results available, but if it is true, it will be a challenge for a comparison of the existing maglev systems. Conclusion, we made an exact comparison, correct and objective, and there is a distortion-free comparison possible based on system typical effective area. Thanks for your attention.
Thank you very much, Mr. Fritz, for this presentation. First question, or are there any questions from the audience? Maybe you can stand up, say your name, and
okay. You calculated the energy consumption of the high-speed magnet train. We have some data, accumulation data for low-speed magnet. Okay. I think for low-speed magnet, the aerodynamic effect is not so big. So according to our experience, when the magnet train travel faster, the energy consumption is lower because the suspension power is the same. Once they travel faster, the average energy consumption is lower. When the low speed, when we use for urban mass transit, so the speed is limited to 100 km per hour. If we travel, the travel speed is 60 km per hour, so the energy consumption is the same as the metro. You see, metro travels at 35 km per hour. So if the magnet train travel at the travel station, travel speed of 35, maybe the energy consumption is 50 kilometers. But your case is high speed, so the aerodynamic influence is much higher.
Yes, of course.
So according to our experience, for low speed magnet, for urban mass transit, if the magnet can travel faster, the energy consumption is lower.
Yeah, for a low-speed maglev and low-speed metro systems, suburban systems and something like that, you have to start a new comparison. This is different. Probably you have a short starter system for the maglev trains. I think this is not comparable with the results for high-speed maglev trains. You can compare the conventional systems, of course, a metro system with a high-speed train, but it makes no sense with this background.
All right. One last question. And after this question, I would like to hand over to the next presentation due to the short amount of time.
Рынков Дмитрий, Петербургский государственный университет путей сообщения. В своем докладе вы сказали о том, что рассматривали системы высокоскоростные.
I'm sorry, we need an English presence. Please again.
Вы говорили о том, что рассматривали высокоскоростные транспортные системы. Number one.
Is it possible that we shift the question afterwards, that you contact him directly, because we have a technical problem with the translator.
I can't hear.
Is it okay?
Okay.
Yeah.
We can discuss it.
I'm sorry.
Okay.
Maybe you can go direct to him. Okay, due to the time, I would like to introduce the next presentation. The presentation will be given by Mr. Arthur Wallach. He actually works for Atkins SNC Lavalin. He's a structural engineer with a large railway experience, and he will give us an overview about the maglev freight, one possible path forward in the USA.
Здравствуйте. My presentation is maglev freight, one possible path forward in the United States. As Mr. Blow mentioned to you a short while ago, there's not much happening right now in the United States in terms of maglev, especially maglev freight. So my talk is about one possible way forward for us in the United States. Now, the United States has 25% of the world's rail routes. So whatever we do in the United States with our rail routes will have tremendous impacts on our economy and a lot of other things. However, with maglev freight, it will be difficult to justify investing in a new intermodal freight system in the United States because we have such an extensive rail and highway infrastructure already in place. Here you also see one of the world's largest rail yards, which is owned by Union Pacific Railroad. Sorry, here we go. Transport worldwide uses about 25% of the world's energy. Now, the latest data shows that more energy is used to transport people than it is more energy is used to transport goods than is used to transport people. Now, about 12 years ago, I took a class with Professor Bud Griffiths. I don't know if any of you have heard the name, but he was involved with the maglev 2000 system at Brooklyn Polytechnic, which is now a different school. And so he was very much involved in the system. That's also where I had my start in my maglev studies. But I was always more interested in freight, so my interest stayed with maglev freight. Now, the existing trends in cargo transport in the United States are basically that the U.S. rail network is significantly underutilized, and only 3% of the transport energy used for rail operations. At the same time, the U.S. highway system is overstressed, with about 60% of the transportation energy used for trucking and shipping via highways and roadways. Now, in the United States, we also have the largest highway system in the world. But we also know that cargo shipments using trucks are much less efficient than using rail. And also, all this stress on the highway system results in a lot of traffic and congestion which is also a tremendous waste of resources, time, and energy. So what are the future trends in cargo transport in the United States? Well, again, we have a rapidly growing demand for moving cargo by trucking. We have an increasing number of major distribution centers, this is due to online, the marketplace such as Amazon, which just, I think today, exceeded $1 trillion. On the other hand, we have a sluggish demand growth for freight shipments using railways. The slower transport speed for rail makes it less attractive for various types of cargo. But there are a lot of benefits to increasing the demand for rail cargo. So how can we supercharge our freight rail shipping so it will compete better with the highway system? Well, one way, one way is, looks like one slide got deleted, I'm sorry. One way is maglev freight. The positives of maglev freight is that it will be even more efficient than traditional freight rail transport. It's high speed and low noise, and it will be lower maintenance and will have longer service life because there's no mechanical parts, theoretically. Now, the negatives of maglev freight is that it needs its own infrastructure. Test trucks are very expensive, and it is as Mr. Blow had mentioned before, it's really not viable without massive governmental subsidies. And also, prototype testing could take many, many years. Now, partially magnetically levitated freight is designed to be compatible with the existing railways, which true maglev freight would not be. It will still be higher efficiency than conventional freight rail. It will be higher speed and will make better utilization of the railways. It will enhance safety and redundancy. It will also improve as technology advances, but it does not need a quantum leap to be implemented. So in other words, we already have the technology to start working on this tomorrow. Previously proposed solutions to modify existing rail lines to utilize maglev had significant obstacles. I had mentioned the maglev 2000 system previously, where the vehicles could travel on both planar and vertically mounted aluminum loops. But because certain parts of our rail infrastructure could not accommodate that system, it really did not move forward very much. Now, the basis of the PMLF concept is to utilize magnetic levitation technology to assist in transporting freight on existing railways by reducing mechanical contact forces between wheels and rail. PMLF cars and locomotives will have superconducting magnets that will induce currents in track-mounted loops embedded in pre-stressed concrete panels, and this will generate repelling forces, which is similar to what the maglev 2000 system proposed. PMLF trains will be able to travel faster on sections of track that have been upgraded to allow magnetic levitation, but also PMLF trains will revert back to full mechanical wheels on rail mode in order to travel on unmodified sections. Now, there are three main phases envisioned for this PMLF project. The first phase is to implement partial magnetic levitation. The second phase is to integrate magnetic propulsion and guidance. And finally, as all three of these systems are developed and enhanced over the years, eventually we'll hope to get to phase 3, which is to utilize 100% maglev mode of operation on existing US railways. Now, modifying existing railways to accommodate PLF has some challenges, but there are many components that will be very easy and simple to modify. The track will probably be the easiest, and this constitutes over 95% of the railway infrastructure in the United States. Road crossings will also be easy to modify. Utility crossings will be relatively easy to modify, and also bridges and other structures will be easy to modify. And I have, you can see little green boxes are showing up next to the rails. Those are the proposed aluminum loop concrete panels, or other metals could be investigated as well. And you can see how the concrete panel with loops will mount easily to the track system. However, there are components that will be very, very difficult to modify. So these will be such as turnouts, which is shown in the graphic, and the railway crossings and other components. But the positive aspect of the PMF system is, again, it could revert to pure track operations to go across these components that have not yet been modified. So in this graphic, on your left, you see the typical track, which is fairly straightforward to modify. But on the right, you'll see switches and turnouts, and that will be a challenge to modify all those. This is a typical grade crossing, and this will also be relatively straightforward to modify. We'll simply take out the concrete and replace it with the concrete loop panels. A success of the PLMF system will depend on the ability of the system to be integrated within the existing railway infrastructure. PMLF must not adversely affect the operational safety of the railroads, the movement of other trains, the maintenance and restoration activities, and also effects on people in commuter and passenger trains. Now, as far as railway safety and PLMF implementation, positive train control is being implemented in the United States. It was supposed to be implemented by now. The next deadline is this December, but the ultimate deadline has been set for December 31, 2000. Essentially, PTC is designed to prevent train accidents attributable to human error, and it will improve the operational safety of both freight and passenger rail. PMLF will be fully compatible with positive train control because it is based on existing rail infrastructure. And this is a schematic showing your typical positive train control architecture. Now with PTC, positive train control, we still have accidents that are happening, especially at crossings because PTC has no control over vehicles that are trying to cross railroad crossings. With PMLF, we can introduce other safety features, especially railroad crossings, such as scout vehicles. This is a utility vehicle, but you can envision a scout vehicle that travels ahead of the train that stops at railroad crossings to make sure nothing else gets on the tracks. But finally, the last thing we have to be mindful of is that PMLF will have to be fully integrated with the maintenance, repair, and restoration activities that exist on the railroad. Each activity will need to be evaluated individually in terms of how it affects how the PMLF hardware, how it could be affected by partially magnetically levitated freight trains, and how it needs to be modified in the future to optimize the dual use of the railway system.
Mr. Wallach, I'm sorry, but I'm the devil of the time, and the time is almost over.
Thank you very much. And
thank you very much for the interesting presentation. Nevertheless, I would like to let the audience maybe request one question. Is there any question, actually? If not, just contact him directly, and due to the time, I would say thank you for the presentation and would like to introduce you the next speaker.
Спасибо.
Okay, we make the deal that we just go on with the next presentations. Due to the time reserve we actually achieved, I would like to introduce Mr. Wanming Liu. He is from the Tongji University in China, and he worked there as a system engineer and expert for high-speed railways and high-speed maglev. Mr. Liu, also when we achieved a couple of minutes, I would like you to give the presentation within the time slot. I know you have 2 presentations, so in total we have almost 1/2 hour from now, and the audience is yours.
Yeah. The topic of the system comparison is old topic for I think about 20 years. But today, what I want to say is problem China first for how to develop the maglev transportation for the further application. So.
Just speak here, and you see the slide.
Oh, so, yeah.
So just
Yeah. So the problem we faced is how I think. This is the second one. That is the first one. According to the program, the first presentation will be the program Chinese first, how to put the maglev translation for the development. The second one is the comparison. Now I make this the second one first, the comparison for of the 2 systems. So this topic is a very old topic. I think many countries and many scientists have done such a comparison. But I think China is the only one country with both the 2 systems in commercial operation. Our experience may be interesting for maglev professionals. So the comparison will be carried out in different subsystems. At first is the infrastructure construction cost. This cost were decided by the three factors: the load or to the track, girder, and the fundamental, and the manufacturing and installing accuracy requirement, and the allowable settlement. This affects the structure and the size of the track, load bearing, and the structure and the function, and then decide the contract cost per unit length of the line. And then another factor, very important factor, is the line parameter of the system. This affects the quantity of civil engineering work and then the engineering cost. The comparison are based on the existing Chinese technical standard or the technical regulation. The two systems have close requirements for foundation settlement and lateral deformation. At present, the length cost of high-speed maglev track is about twice of the high-speed railway. But the track structure of the high-speed maglev has been researched to be greater obvious simplification, and the cost will be greater decrease of about 1/3. From the viewpoint of the train running load, this is the load index from high-speed railway and high-speed maglev. We can show the load of high-speed maglev is somewhat lower than the high-speed railway. So, from the viewpoint of the load, the high-speed maglev may be somewhat lower than the high-speed railway. But the deformation requirement, the high-speed maglev is more stricter than the high-speed railway. So, you can see the deformation regulation. So from the two sides, we can see the civil engineering cost may be the same. This is the stiffest requirement of the track beam. According to a simple design, we can calculate the cost of a straight line with a 25-meter span. The high-speed railway may be 7.556 million RMB per kilometer, and the maglev may be 6.019 million RMB kilometer. So the construction cost of the elevated structure of maglev is comparable to the high-speed railway. Another comparison is from the alignment parameter. So this is from the design code of the Chinese standard. This is the maximum radius of the curve. Through a study, we have made a test alignment. We can see the civil engineering work difference between the maglev and the railway. Compared to the high-speed railway, the total length of the line reduced about 3%. And the twin tunnel length reduced by 86.5%. So the civil engineering costs reduced by 23%. We can also see the case study from the German side. For the burning Hamburg line, the civil engineering cost by this project is about the same. Although the train of the maglev is much higher, the cost is much higher than the high-speed railway. But for the same turnover, just as for the same work, the train purchase cost may be the same or somewhat cheaper than the high-speed railway. This is a comparison of the cost. Another question is about the adaptability in the passenger transport. We established a leasing model. This is the utility. This means if the value of the passenger is during the saving to 31.4 RMB per hour, this is the critical difference. Critical difference. That means if the value of time is lower, it is better to build a high-speed railway. If it is higher, it is better to build a maglev. So. The unit cost of the infrastructure of maglev is about twice of the high-speed railway at ground, but for the elevated line, it is similar. The overall cost of infrastructure is dependent on the terrain. In plain area, the maglev is about 20% higher, but in mountainous area, it is about 20% less. The seat price of the high-speed maglev train is 48% higher than that of the railway, but the total purchase may be the same. In plain area, the operating expenditure of maglev is slightly smaller than the high-speed railway. In hill or mountainous, its advantage is more obvious. The best choice to set a high-speed passenger system is dependent on the economical level of the corridor. If the average time value of the passenger is lower than such what, it is better to build a railway. Otherwise, it is better to build a maglev. That's up.
All right.
This is the first one.
Thank you, Mr. Liu. That's your applause. All right. The first question belongs again to the audience. Is there any question to this presentation by Mr. Liu? If the audience has no question, maybe I may ask a question. You mentioned the value of time.
Yeah.
How did you calculate this? Is it more a value which belongs to feelings, or is it have it a commercial background, or how did you decided to introduce such a parameter?
The value of time describes the pain winning of the passenger. It can be calculated from the economic data for income and such economic data. It also could be through the survey for the public, so we can get the pay winning of the passenger for such payment. Yeah.
Understand. That means, in this case, if you're when you have much more money as a passenger, you quite probably choose the magnetic levitation or the aviation in this case. All right. Okay. Maybe during this time, is there any new question maybe by the audience? Professor Klüspies.
Thank you for your presentation. Did you calculate about the tunnel influence of tunnel comparison maglev HSR? Did you compare?
About the tunnels, I think for the maglev, the design speed is much higher than the railway, so it needs more gross area. So may it be somewhat expensive for the railway, but through the flexible line parameter, we can avoid to build more tunnel. Yeah, that's the question.
All right, thank you for the answer, Mr. Liu. Is there any other question? As you remember, we lost one presentation, thus we have a little bit more time. If not, I would just hand over to the next speaker, and he's already here. So the sheet says Mr. Liu will also talk about the development prospects of high-speed maglev and high-speed rail area. And for those who come a little bit later, Mr. Liu is from the Tongji University, and he is a system engineer. Okay, Mr. Liu?
Yeah.
Good luck for the next presentation.
It's grateful to give me more time to report my study of my work. Yeah, the second topic is the development prospect of high-speed maglev after high-speed railway era. This is the content of this presentation. The problem for maglev application in China, I think you also, the operation of maglev have been 50 years. It is proved to be safe, reliable, and available. And the most spare parts can be manufactured in China. And we also developed a new generation of train. This new generation train was manufactured 4 years ago. So we can see the high-speed maglev technology is ready for further application. But we meet a question, meet a problem, no place for building maglev. In the past 50 years, China has established a huge and dense high-speed railway net. Up to end 2017, about 25,000 kilometers in operation and more 13,000 kilometers high-speed railway under construction. The total length is twice of the sum of all other countries in the world. So, the high-speed railway net has reached every city and towns, with a population more than 500,000. That means everywhere is a high-speed railway. Where is still need maglev? This is a question many people think, and most of our maglev professional is also think of this problem. So my viewpoint is to set a maglev network by upgrading existing high-speed railway line. That means we can upgrade the high-speed railway from the speed of 250 and 350 to a maximum speed of 500 kilometers. Is this sort reasonable? So we think the designed life of the foundation column and the beam is 100 years, while the vehicle is only 30 years. The cost for civil engineering is about 70% of the whole system. It is still useful once the vehicle reaches their service time. By the end of the service time of high-speed rail train, substituted them with a high-speed train. Thus, a high-speed maglev system is built without new land purchasing and engineering demolition, and in shorter period with less cost. In order to realize our thinking, what should we do? We must do the technical confirmation and the economical estimation. We should check the adaptability of the high-speed railway line to the maglev train. And we also should check the adaptability of the operation load for the structure, and the aerodynamic check for a maximum speed of 500 kilometers. And how much device of the power supply system can be reused, and how much device of the operation control system can be reused, and how much is the cost for such upgrading. Through our study, the result is as follows. For the alignment and the civil engineering structure, the radius of horizontal and the vertical curve is okay, but the transit curve cannot meet the demand of maglev. But the adjustment can be done without moving the column and the beam. Under the maglev load, the vertical deflection of the existing beam meets the requirement of maglev on most occasions, but sometimes it is not okay. Adjust or replace of beam is very seldom. This situation takes place by as the designed speed lower than 250 km/h for the existing level. The maglev has stricter requirements on settlement and deformation, but this can be solved by using adjustable bearing. The clearance is okay at open track. In tunnel, it is unable to reach the maximum speed. If we don't like so, a nano car body is needed. So, Ms. Chris Picker has asked this question. The functional parts of the track and the switch must be replaced. For the vehicle, the car body of railway does not meet the requirement for the maximum speed of 500 km. And its mechanical strength is also cannot meet the requirement. Due to different running mechanism, the infrastructure of the railway vehicle should be totally given up. The existing maglev vehicle with a weight of 3.7 meters is not available to running in tunnel with the designed speed 500 kilometers. So it should be with the same or less weight like the high-speed rail vehicle. This means if we want to use the maglev on the existing railway, we must adjust the weight of the maglev vehicle. For the power supply system, due to different technology of propulsion, the wayside device should be replaced. But the fundamental power supply device, for example, the substation and the power cable for outer input can be further used. The power supply system needs more ground space to set equipment. The existing railway right of land is adequate. For the operation control system, due to higher level of automation and information, the most devices, including hardware and software, should be replaced. Some fundamental equipment, for example, the communication, can be further used. For other equipment, such as the passenger information, station service, and the eternity can be greater used. The cost we have calculated it is about 52% of the new built maglev. So the conclusion, this think the upgrading is technologically feasible. Such upgrading can improve the running speed from 250 or 350 to 500 kilometer. This service level can be greatly enhanced. Through such upgrading, we can establish a maglev system with lower costs, no new land resource, short construction period. The research shows that even after a large-scale construction of a high-speed railway, the maglev technology has still great application space. Thank you.
All right, thank you, Mr. Liu, for this presentation. Same procedure as for every presentation. Are there any questions by the audience? If this is not the case, first of all, I like the solution approaches of the Chinese people. When I just read that there's no place for high-speed maglev, I just want to say tear down high-speed rail and just build it. But at the end you showed us that it is generally feasible to install high-speed maglev. Yeah. I'm an electrical engineer, and my question would be, how do you handle the propulsion system? Usually for high-speed railways, the propulsion system is on the vehicle, and for high-speed maglev, you need to install the propulsion system along the track side. Did you make any investigations in this matter to install the propulsion system along the line?
Propulsion system?
Yeah, the motor.
Yeah. The motor,
the motor of high-speed maglev.
The propulsion system has a larger portion of the whole system. So this is also the problem we need to pay for such upgrading.
Okay. And who will develop the propulsion system? Will it be done by the universities, or will it be done by CRRC or a different company?
For the propulsion system, it is handled by the Chinese scientific institute.
All right, so you have, this is an institute by the university, maybe from the Jiangzhou University or a different university?
Not from the university, it's from the institute.
Ah, okay.
The Chinese Scientific Institute is the highest level research.
Okay, understand. Thank you very much. Last questions. Okay, we have just a second. I saw you, Mr. Lascher, but before I ask you, the hand there was much faster. So, just a second.
Okay, thank you for your presentation. You mentioned that the diameter of the tunnels was not adequate to run this current system on high speed. So, on what speed would be the limit for the current system? So, what speed reduction are you talking about if you run through the existing tunnels?
Hard job.
Sorry, I'm not very clear. What's the problem?
He wanted to know what is the speed limit if you use the existing tunnels for high-speed maglev.
Yeah. So because of the aerodynamic factor, the faster the train running, the more cross-section area should we need. So if we running the maglev in the existing railway tunnel, we should develop a new type of maglev vehicle. It should be nano than the railway vehicle. So we get the design speed.
So I think what you want to say is when you have maglev vehicles which have a much larger cross-section compared to the tunnels, you need to reduce the speed, definitely. But the number or how much the speed needs to be reduced is actually not investigated. So it needs to be done.
Yeah.
Okay, so Mr. Lascher, a short question because I would like to keep in time.
Also meine Frage kommt auf Russisch, ja, geht oder nicht?
Russisch ist schlecht, Englisch wäre besser, weil das Audio, wir haben jetzt...
Oder Deutsch, Deutsch auch geht nicht, ne? Kein Russisch, kein Deutsch? Übersetzen Sie bitte.
Okay, I try to translate.
In dieser Präsentation, in Ihrer Präsentation,
I want to translate. I try to translate. Okay, in your presentation...
in Ihrer Präsentation sagen Sie, dass wollen Sie Bahninfrastruktur von Hochgeschwindigkeit Railway-System für Magnetschwebetechnik nutzen.
In your presentation you say you want to use high-speed railway infrastructure for high-speed maglev. Yes.
Ja, auf Basis Ihrer Abbildung merke ich, dass nutzen Sie Elektromagnetschwebetechnik.
So you are using electromagnetic suspension, so similar to the transrapid technology? Yes. Yes. The German system, the formerly German system.
Und wissen Sie vielleicht, dass Elektromagnetschwebetechnik hat diese Luftabstand circa 10 mm.
So the air gap for... Okay, so the question is?
Ja. Und in Deutschland für solche Systeme, weil muss ganz bezüglich Fahrdynamik solche Systeme braucht keine flexible Fahrbahn. Also muss starr sein, dann nicht kein Unfall passiert, weil
So the requirement for the track beam is that it needs to be stiff because you have only a small air gap between 8 and 12 millimeters.
yeah.
And the question? And the question? Once again, the question.
In Deutschland wurde entwickelt 3 Varianten von Infrastruktur: Beton, Betonmetall und Metallkomplett. Und diese Fahrbahn, ist Infrastruktur ist ziemlich teuer. Also das ist ein großer Teil vom gesamten Verkehrssystem. Für Fahrbahninfrastruktur das ist ein großer Teil vom gesamten Verkehrssystem.
Herr Lascher, die Frage. Jetzt.
Meine Frage.
The question now.
Diese Aussage, dass Eisenbahnverkehrsinfrastruktur passt für Elektromagnetschwebesystem, wurde das experimentell getestet?
Did you already made some experiments, or is it just a theoretical approach of your analysis? Actually, is it just theoretical, or you just tried to shift maybe a small test track from high-speed rail to high-speed maglev? No. Time's up. Your answer, please.
We checked. We check from different subsystems. So such a check are based on the existing Chinese technical standard or technical regulation. So I think it is theoretical feasible. Now we don't.
Actually, it's just a theoretical. We got your question, Mr. Lascher. I would suggest just to sit down, and for further questions, I would suggest to go after the presentation. No, stop. No, stop. The time is almost up. I would suggest that you contact Mr. Liu. He will be available today in the evening as well as tomorrow, and you can talk to him directly. We need to keep in time. Mr. Liu, thank you very much for the presentation once again, and. I'm quite sorry, but I need to hand over to the next presentation to keep in time. Thank you very much, and we will see us. The next presenter is Mr. Andrei Nikolaev. He is from the Fund of Magnetic Levitation Transportation in Russia. Mr. Lascher. Mr. Lascher, please sit down. All right, sorry that I need to disrupt you, but it would be great when you don't disturb the audience, or just make the small talks during the break or after the session. And I think Mr. Liu will answer your question. So once again, welcome, Mr. Andrei Nikolaev. He is from the Fund of Maglev Transportation, Russian, and he will give us a presentation about the magnetic levitation transport as an instrument for innovative transformation of spatial structure of urban agglomeration. Thank you for being here, and the audience is yours.
Добрый вечер. Я благодарен организаторам за возможность выступить перед вами. Для эффективного развития магнитолевитационного транспорта, который мы считаем самостоятельным видом транспорта, как известно, нет ничего лучше, нет ничего практичнее хорошей теории. Поэтому мы считаем необходимым определить место магнитолевитационного транспорта в пространственной структуре. Мой доклад будет посвящен как раз рассмотрению пространственной структуры городов и городских агломераций. Доля мирового населения, проживающего в городах, неуклонно растет. Урбанизация является одним из доминирующих социально-экономических процессов современности. В период с 50 по 2015 год глобальное городское население увеличилось более чем в 2 раза. В то время как процесс урбанизации значительно замедлился в более развитых странах, в развивающихся странах он идет ускоряющимися темпами. Этот процесс сопровождается значительными всплесками в требованиях городской мобильности. Тенденция роста размеров городов и увеличения доли урбанизированного населения, как ожидается, неизбежно продолжится во второй половине 21 века. К 2050 году практически 6,5 миллиардов человек, или около 2/3 человечества, вероятно, будут городскими жителями. При этом основная масса городского населения будет сконцентрирована в мегаполисах и городских агломерациях. С учетом вышеперечисленных тенденций, проблема развития городского транспорта имеет первостепенное значение для обслуживания пассажира и грузопотока в городах и городских агломерациях. Таким образом, мобильность становится ключевой движущей силой урбанизации, а связанная с ней инфраструктура формирует городскую среду, то есть пространственный отпечаток, определяемый транспортной системой городов. Стандартным ответом на решение проблем городской мобильности, как правило, становится увеличение инфраструктуры, в основном для автомобилей, таких как строительство большого количества дорог, автомагистралей, эстакад и тоннелей. Эта деятельность порождает порочный круг. Расширение инфраструктуры стимулирует разрастание городов, поскольку облегчает доступ к периферийным городским районам, расширяется использование автомобилей, что в свою очередь требует дальнейшего развития инфраструктуры, автомобильной инфраструктуры и так далее. Как показывает мировой опыт развития городов, мобильность, ориентированная на автомобиль, не позволяет обеспечить требуемый уровень транспортного обслуживания городских жителей. Важнейшим показателем, характеризующим развитие современного города, является развитость общественного транспорта. Чем выше охват городских территорий общественным транспортом, тем выше интегрированность различных частей города и выше подвижность населения. Безусловно, существуют города, изначально ориентированные на автомобиль. Это сравнительно молодые города Северной Америки, Канады и Австралии. таких городах свыше 60-70% городской площади занято под обслуживание автомобилей, улично-дорожная сеть и парковочные места. Нам представляется, что это недоступно высокая цена для современного города. В настоящее время возникла насущная проблема осмысления функциональной роли каждого вида транспорта в транспортной системе современного города. Пространственная структура городских агломераций сложна и многообразна, но при этом она может быть классифицирована по критерию плотности застройки городских пространств. Данный критерий представляется ключевым при выборе направления развития скоростных видов городского транспорта. Бесспорно, основным видом скоростного транспорта в центральных районах городов является метрополитен. Но метрополитен также является самым дорогим видом транспорта, что является основным препятствием для его распространения. В настоящее время повсеместное распространение получило тенденцию задействовать существующие дорожные пути для организации пассажирского движения. В целом с этим можно согласиться, но с одной оговоркой – это существующие пути в рамках существующих транспортных коридоров. Создание новых линий внеуличного транспорта за счет строительства новых дорожных линий в черте города невозможно по вполне понятным причинам. В первую очередь земельным, которым обязательно необходимо добавить еще экологические. Дорожный транспорт – это самый шумный из всех видов транспорта, используемых для городских пассажирских перевозок. На этом перечень внеуличных видов транспорта заканчивается. Как видим, этот перечень очень невелик, при том, что есть общее понимание необходимости опережающего развития скоростных видов общественного транспорта. В настоящее время ренессанс переживает трамвай, который пытаются сделать неуличным видом транспорта. Хотя правильно сказать, что его усиленно реанимируют, пытаясь создать что-то промежуточное между дорожным транспортом с его скоростными и провозными характеристиками и традиционным трамваем, тихоходным и малопроизводительным. Следует напомнить одну из основных причин отказа от традиционного трамвая, кроме шумности, тихоходности и так далее. Это то, что трамвайные пути пролегают по улично-дорожной сети. В результате трамвайное сообщение становится частью дорожного движения и ограничением для движения автомобилей. И данный факт является основным слабым местом трамвайного ренессанса, так как автомобилизацию никто не отменит. Использование автомобилей для жителей города очевидно связано с множеством преимуществ, таких как мобильность, комфорт, статус, скорость, удобство и так далее. Эти преимущества совместно иллюстрируют, почему количество автомобилей продолжает расти во всем мире, и особенно в городах. Ко всему прочему, владение и использование автомобиля является символом статуса. Когда представляется выбор и возможность, большинство людей предпочитают использовать автомобиль. Необходимо понимать, что автомобилизация является объективным фактором городского развития, пока не возникнет общественный транспорт с аналогичными потребительскими характеристиками. В результате указано совмещение все виды общественного транспорта, осуществляющие перевозки пассажиров по улично-дорожной сети в городах, автобусы, троллейбусы, трамваи испытывают те же самые сложности передвижения, что и личный автотранспорт, и не способны оказать приемлемые по качеству транспортные услуги населению. Внедрение выделенных полос для дорожного движения общественного транспорта позволяет повысить эффективность общественного транспорта, но в результате дискриминации подвергаются жители городов, использующих личный автомобиль. Таким образом, необходимо признать, что развитие существующих видов скоростного городского транспорта не решает потребности жителей городских агломераций в мобильности. В настоящее время в городах можно ответить два практически взаимоисключающих тренда с точки зрения повышения мобильности населения. Первое. Развитие улично-дорожной сети, включая строительство автомагистралей, повышает привлекательность личного автомобиля, соответствующее повышению индивидуальной мобильности жителей. Второе. Развитие общественных видов транспорта, например, автобусного сообщения, созданием выделенных полос сокращает пропускные способности улично-дорожной сети, что приводит к обратному результату. Но на этот же результат решает развитие системы платных парковок. В продолжении темы трамвая необходимо отметить, что из него маловероятно удастся сделать полноценную внеуличную транспортную систему, в связи с тем, что города имеют плотную застройку, и выделение площадей по транспортной инфраструктуре всегда проблематично. Как нам представляется, необходимо обратить внимание на ключевой фактор оценки любой городской транспортной системы – это транспортная безопасность. Наземные выделенные пути скоростного трамвая должны быть надежно защищены от проникновения. В результате разрушается целостность городской транспортной среды, разрезанной трамвайными путями. И как следствие возникает необходимое строительство разноуровневых пешеходных переходов и автомобильных переездов, что оказывает существенное влияние на общие затраты по созданию линии легкорельсового трамвая. Выше приведенный экспресс-обзор показывает, что в настоящее время не существует транспортной системы, удовлетворяющей современным требованиям и не требующей ущемления других видов транспорта для своего развития. По этому поводу можно привести высказывание Уинстона Черчилля: «Генералы всегда готовятся к прошлой войне. Все транспортные системы, используемые и развиваемые в настоящее время, имеют практически вековую и более историю, и в целом уже перешли пик своего развития или его достигли». Нам представляется, что для современных городов многомиллиардные инвестиции в развитие транспортных систем, которые не могут решить насущные проблемы, являются непозволительной роскошью. Города растут. Ежегодно строятся сотни тысяч и миллионы квадратных метров жилой коммерческой недвижимости. Создаются новые центры деловой активности. Актуальнейшей задачей является обеспечение новых городских районов скоростным общественным транспортом. В то же время существующие транспортные коридоры, как железнодорожные, так и автодорожные, практически исчерпали свои провозные способности. Мы убеждены, что магнитолевитационный транспорт является ключом городом будущего. Располагающиеся на эстакадах магнитолевитационные поезда смогут пересекать любой городской и природный ландшафт без ущерба для него. Динамические характеристики МЛТ позволяют устанавливать любой скоростной режим, удобный для качественного обслуживания жителей. Мы уверены, что за исключением центральных деловых районов с их высокой плотностью городской застройки, магнитолевитационный транспорт станет основным видом скоростного общественного транспорта на территории городских агломераций. Спасибо.
Спасибо большое. Mr. Nikolaev, same procedure as for every presentation. Is there any question from the audience? I look in this direction. Urban maglev transportation. Okay, so then I will start maybe with the first question. We learned that with maglev you can influence urban growth and settlement. How is the support of the actual Russian government towards maglev support? Are there special committees or something? Or the second question is, when you would have a wish, what would you address to the Russian government to support maglev projects? Maybe also to Mr. Zaitsev.
Здесь присутствует наш идейный и научный руководитель Анатолий Александрович Зайцев. Он уже произносил эту фразу, что, к сожалению, мы в России мало получаем поддержки как от правительственной структуры, так и от национальных корпораций. Боремся.
Спасибо.
Спасибо.
Is there any other question right now? If not, then I would say this session is over for transport system. So, and before you leave, I would like to address some words to you. First of all, a big thank you to the organizers. I think it was a quite successful first day. And I also would like to thank the people behind the scenes. And the people behind the scenes are sitting in this booth. Two ladies who made the translation. That means they talked the entire day. So the applause is yours. And the committee just requested me to give you an information for all participants. The university area is quite large, and those of you who are attending the rector's reception party, please go to the reception hall until 17:45. So I think it's about 15 to 20 minutes. Go to the reception hall, and then we all will go to the reception party. And please don't forget your reception invitation of those who are invited. For the guys who maybe visit St. Petersburg, have nice impressions, enjoy maybe the local scenes, and yeah, just get in contact with colleagues. And yeah, latest, see you tomorrow. Thank you very much, and the session is closed.